Today's lesson is on using matrices to solve systems of equations. We're going to look at how we can do that. We've already done substitution and elimination as methods for solving systems of equations, and now we're going to look at how we can use matrices. We're going to start with this example. We have here a 2 by 2 system of equations, x plus 2y equals 2, and negative 4x plus 3y equals 25. And we want to take the systems of equations and write it in the form of a matrix equation, ax equals b, where A is the matrix of coefficients, and we just pick off the coefficients of the variables in the equations and write them in the form of a matrix. So we'll have 1, 2, negative 4, and 3 as the elements of matrix A. Matrix X is our matrix of variables, so we put them in the same order that we see them here, so it'll be X, Y. And B is our matrix of constants, and you may need to rearrange the equations before you can write these matrices because you have to have your equal signs and your variables all lined up. And the matrix of constants then is 2 and 25. So as we write that into a matrix equation, we then get matrix A times matrix X gives us matrix B. And we want to solve for matrix X because once we've solved for matrix X, we know then the values of X and Y. So let's look at the matrix equation first, AX equals B. When we solved matrix equations previously, we first isolated X and then we did the algebra on the rest of the values. So to isolate X, this is A times X. So we need to reverse that operation, and the way we can do that is by multiplying both sides of the equal sign by the inverse of matrix A. Okay, and the reason we can do that is that A's inverse times A gives us the identity matrix, and the identity matrix times anything gives itself. So I times X gives us X. So now on the left side we have matrix X isolated like we want it to be is equal to A's inverse times matrix B. So that means then we can do the inverse. So if you recall from previous lessons, the inverse of a 2 by 2 matrix is given by this formula. Excuse me. So using this, using our original A matrix, we did AD minus BC and got 11. So we have 1 over 11 times, and we switched the places of A and D and switched the signs of B and C multiplied by our matrix B. So we're going to leave that 1 over 11 out front for now rather than doing that scalar multiplication first and needing to work with a lot of fractions. And so now we'll do row by column multiplication here. And recall this is a 2 by 2. This one is a 2 by 1. So those two numbers are equal, so we can multiply, and our result will be a 2 by 1 matrix. So a 2 by 1 matrix, 2 rows, 1 column. So when I take row 1 with column 1, I get 6 minus, just a second here. Okay, I see what I've done wrong here. This should be a 25 here. That's what my mistake is. So I have 3 times 2 giving me 6 minus 50, so I have a negative 44 here. And then when I do the second row, I have 8 plus 25 giving me 33. So now when I multiply that 1 over 11 by that matrix, I end up with negative 44, sorry, with negative 4 and 3. So recall that matrix X is really XY. So we can see that X is equal to negative 4, Y is equal to 3. So negative 4, 3 is the solution. Okay, so let's look at one more example doing this. Here's a 2 by 2 equation, or system of equations rather. So let's turn that into a matrix equation. That will be, our matrix A will be 3, -4, 2, and 3 times xy equals 11 and -4. So there's our matrix equation in the form of A times X equals B. So matrix X will be A's inverse times B. So let's do the inverse of this 2 by 2 matrix. So I've got 3 times 3 is 9 minus -8, so that'll be 17. So I have 1 over 17 times A and D switch places, and B and C switch signs. And I'm multiplying that by 11 and -4. So I have 1 over 17 times, and I've got 3 times 11 and 4 times -4, which will give me 33 minus 16, so it'll give me 17. And then I've got -2 times 11, so -22 minus 12, so that's minus 34. So now when I multiply the 1/17 through, I end up with 1 and -2 as my resulting matrix. So 1, -2 is the solution. For 3 by 3 systems, we're going to use technology, but the same method applies. So we're going to multiply, we're going to look at a system of equations first of all. So in this example, we have these 3 equations with the 3 variables. We're going to turn them into an equation in the form of A times X equals B. So to solve for X is going to be A's inverse times B. Now, on the handout that's also available on Moodle, you'll see the graphing calculator instructions for entering matrix A, entering matrix B, and then for doing the multiplication. A couple of notes about doing that. When you enter the matrix, so you're going to go second and matrix to get there. When you enter that, you'll see across the top names, math, and edit. You'll always use the edit column when you're creating or changing a matrix, whether you want to change its size or change the elements within the matrix. When you want to create the matrix equation, when you want to do math with it, you leave the cursor on names, and so that will just bring up the name. And the button on the graphing calculators for doing the inverse looks like this, x to the -1. So give that a try with either a graphing calculator simulator or with a graphing calculator if you have access to one, and try that. And we will have graphing calculators available in class for you to do this with as well. So when you enter matrix A into the graphing calculator, then you'll use its inverse and you'll multiply that by matrix B. And when you do that, you'll get, as a result, 26, -5, and 3. So that X is equal to 26, Y is equal to -5, and Z is equal to 3. And you'll see, once you've got a little bit of practice with this, you'll see that it's a very fast way to solve a 3 by 3 system. If you turn in your book to page 781, number 33, there's a question there about selling tickets. And so I'd like to just work through that solution to that problem using the inverse matrix and using the technology available to us to do that. So our first step in solving that problem will be to state what our variables are. So we can say let A, B, and C represent the numbers of $8, $10, and $12 tickets respectively. Then from the information in the problem, we can find our 3 equations. So the first equation is based on the fact that we know that 400 tickets are sold altogether. The second equation is based on revenue, so the $8 tickets are multiplied by 8, the $10 tickets by 10, and the $12 tickets by 12 to get the total revenue of $3,700. And then we know that A plus B is equal to 7C from that last sentence in the problem, which we will rewrite that equation so that it lines up with the other ones to be A plus B minus 7C equals 0. Once those equations are rewritten now, we can see that we have a matrix equation of 1, 1, 1, 8, 10, 12, and 1, 1, negative 7 times A, B, C, the variables that we declared, equals 400, 3,700, and 0. So if we call that A times X equals B, we can then determine that matrix X is equal to A's inverse times B, which with the calculator will give us 200, 150, and 50 as a result. So then we can just state that they sold 200 $8 tickets, 150 $10 tickets, and 50 $12 tickets. And we're finished. So on that handout, you'll see a number of word problems as well. So give those word problems a try. Even if you're not sure of the calculator steps, see if you can come up with the 3 equations and the 3 variables in those examples so that when we practice with the calculators on Tuesday, you have lots of time to play around with the calculator in order to get that skill down pat.